Chapter 8, getting ahead of myself, we're going to start the basic concepts of chemical bonding. Okay, the first thing we're going to talk about is the three types of bonding there are. First off, in ionic bonding, the electrons are transferred. So when you transferred the electrons, then you form ions. So the bond is electrostatic attraction. What that means is you end up with positives and negatives, and they're attracted to each other. So this tends to be a non-metal bond, and it's a non-metal metal because the metals form the cations and the non-metals form the anions, and then they come together with their charges. Okay? Second type, and the one that we're going to spend the most time in the next two chapters, we are going to do some ionic bonding stuff, but the majority of it is going to be the covalent bonding. That's when the electrons are shared. Molecules are formed by the overlap of orbitals, and this is where you have non-metal bonds. So these occur only with nonmetals, and they're the huge class that usually involves organics, etc. So that's a huge class, and again, we'll talk about those in detail. Now, metallic bonding, we're going to spend the least amount of time. Metallic bonding is known as a sea of electrons, and it's only involved with metallic metals and metals forming bonds with each other, and we'll spend one or two slides on it, may only be one, I can't even remember, and then we will be done with metallic bonds. More about that in just a minute. Okay, so the general trend is metal and non-metal will be ionic. Non-metal and non-metal will be covalent. Now, of covalent bonds, you're going to find out that we have pure covalent bonds and we have polar covalent bonds. If you have metals bonded with metals, brass, etc., that's a metallic bond. So this is just a recap of what we did before. So we're going to talk about metallic bonds. In metallic bonds, atoms are packed in a 3D array. What that means is we're going to call it a sea of electrons. And the electrons are delocalized. That means that they're shared among a number of atoms. So the easiest explanation of this is take a small aquarium, a square one, it could be a round one, don't care. Picture a small aquarium, pack it with marbles. Those are the nuclei of all the metals. Now pour in water. So the water moves all around the nuclei. So that's why the electrons are called the sea, because they're totally delocalized. They're moving everywhere around, but amongst all the nuclei, like the water would move around marbles in an aquarium. What this net effect does is this allows the transfer of kinetic energy, heat, electricity through this array of delocalized electrons. And this is critical for conduction. So for example, if you have wiring, you tend to make it out of metals, not nonmetals, because you have the delocalized electrons in metals. Okay. They also establish conduction bands. That means that the electrons move freely through the subshells. Now, why is that important? That's important again because the conductivity of metals and allows them to transfer stuff. So this is the slide on metallic bonds. You need to know this. You'll be asked something about metallic bonds. It'll be a multiple choice, fill in the blank matching, something like that. But you need to know that the electrons are in a sea, known as a sea of electrons, because all of the electrons are delocalized within the compound. Okay, that brings us to ionic compounds. Ionic compounds form when the ions come together. Remember, you're going to have cations plus anions. And so the positive and the negative come together. They're held together by electrostatic or coulombic attraction. They form extensive 3D arrays. So when you talk about, they're using sodium chloride down here, this crystal can go on as long as it can go on. So they're packed, and it's not like in organic compounds where you have a set number and then you're done with the molecule. These arrays can be really small, as little as 1 sodium, 1 chloride, and can keep going. They're going to transfer electrons when making Lewis structures. More about that when we get to Lewis structures. And they form ions when melting at high temperature. So they tend to be conductors either when they themselves are melted in liquid form or when they're in aqueous form. But the crystals themselves are not conductors. Okay? They will dissolve in water, hence the solubility and salt formation. So that brings us to, oh, I forgot about this slide. I think it was on the History Channel. It may have been Nat Geo. I don't remember. They were talking about this mine in Mexico, and they started pumping the water out. And when they started pumping the water out, they got these humongous, gigantic crystals. These are the crystals that you can form in little crystal sets. But if you'll notice this little guy in the middle here, look at the size of the crystals compared to him. You have to go in with the suit. The temperatures are incredibly high. And so they can't stay in for long to study these, but it's like the perfect crystal formation of all kinds in this mine. And again, these are the same crystals you can see in a little glass jar, except these are massive. It's really actually cool. Okay, yeah, I know I'm a geek, but okay, moving on. Okay, another geek, Gilbert Newton Lewis. He was an American chemist who got the Nobel Prize because he came up with the bonding. And you're going to use valence electrons to form a compound. And in this case, what happens is that the electrons will be shared in order to form the bond. But there are a couple rules associated with it. The first one is the octet rule. And the octet rule is rather simple. An octet, remember, is 8. So the octet rule states that the atoms share, actually gain is not right, share a maximum of 8 electrons. So when you're forming an octet, think 8, okay? And they're going to share a maximum of 8 electrons, so that means that there are 8 electrons around each atom. Now, I actually started off with gain because we were talking about ionic compounds. Same rule applies there. You're going to try to gain or lose to where you have a maximum of 8 electrons or a minimum number of electrons. And that's why we talked about that when we talked about electron configurations. Okay. So one thing I want to go ahead and point out, there are a variety of ways to write these, but the easiest thing to do is to think of it as north, south, east, and west. And you have a maximum of 2 electrons in each box. Now, there are a couple cases where we'll exceed the octet, more about that later. But the bottom line is if you can keep them in the brackets, it makes your life and my life easier to look at them. All right, so we said valence electrons. What are we talking about? Well, remember the valence electrons are in the outermost shell. Those are the ones filling. So carbon's going to have 4. Calcium's going to have 2. Okay, we can't look in anything that's a filled shell. So arsenic would be 5. Titanium will be 4. So if we were to do the Lewis structures, you can look at them down here. The rule of thumb is you start at one position, it doesn't matter what it is, and go all the way around. You don't double up. Now, this text likes to double up, and so they might write calcium like this, and that's really not following the rules of Lewis structures. The rule states that you start at one point and you go around, and you don't double fill, kind of like Hund's rule, until you get back around. Now, you need to remember that there are a couple exceptions. Helium has a duet. That means it only has 2 electrons. Hydrogen is happy with a duet as well. Okay, and that's because if you look at their position on the electron on the periodic table is where you put the electron configurations, you'll see that it has a maximum of 2 electrons, so it can't go to the octet. And there are a couple other bizarre, weird exceptions. We'll talk about those later. So first off, let's draw Lewis structures. So if we look at vanadium, you're going to find it's going to have 5 valence electrons, so we can write that down here. So we can start at any point. We can go forwards, we can go backwards, doesn't matter. Silicon, if you look, has 4 valence electrons, so it's going to be here. Bismuth, again, has 5 electrons. Again, we can start anywhere we want, keep going around. Bromine has 7, so it's 1, 2, 3, 4, 5, 6, 7. So we end up with 1 lone. Now, you'll notice that I'm using X's. You can use dots. So, for example, krypton has 8, so you could do the dots. As you can tell, my dots are not uniform. I find I'm faster with the X's, but you do whatever floats your boat. Tin has 4 valence electrons, 2 P's and 2 S's. Molybdenum has 6, so it's kind of like oxygen. You're like, wait, it's not anywhere near oxygen. No, it's not, but it follows certain rules because of the number of valence electrons. Aluminium, as the British say, or aluminum, has 3, so it's got 3 there. Now, why is this important? Well, this is important because we're going to need to be able to identify the number of valence electrons and start putting them around the atoms in order to get to the shapes. Now, shapes are very critical when it comes to organic, organometallic compounds, etc. And we'll talk about those in detail. But before we do that, we'll do a small section, which is on the ionic compounds.